So final exam for algebra is scheduled for Wednesday, May 17th, 8:30 to 10:30 in the morning. And that's when the exam will be given, but it will not be in person on campus. It will be online. You take it at home. You'll have 2 hours to do the exam, convert your paper to PDF and upload to Blackboard, just as you've done with homework. And it's an open book exam. You're allowed to use your textbook. Okay, fair enough. And
how many questions will be, Professor?
I haven't the faintest idea. But I've never understood actually why that's relevant, because whatever it is what it is. So there
Okay.
could be 6 questions, there could be 10 questions. There could be 10 questions, but then I make them 5 questions with 2 parts. So is that 5 questions or 10 questions?
Okay. It's
know.
from the, do we have any review for this, Professor?
Yeah, there will be a review. And I have to assign one more homework on rings, which I'll do today, and it'll be due next week. But because rings will be on the final exam. And in fact, what I'm going to do today, since I spoke about rings on Monday and I covered a lot of material, is I want to review what I did on Monday and then solve some problems in the book that are on rings. So today is, if you like, a kind of review of ring theory. And we'll start off with the definition. So again, a ring is a set, let's call it R, with 2 operations, addition and multiplication. That satisfy the following 3 properties. First, under addition, R is an additive abelian group. Second, the multiplication is associative. So xy times z is x times yz for all x, y, and z. And we have the distributive laws are satisfied. X times y plus z is xy plus xz, and y plus z times x is yx plus zx. So that is a ring. You can add and you can multiply. Because R is an additive abelian group, you can subtract. But because R is not necessarily a multiplicative group, you cannot divide in general. But you can multiply. And we say R is sometimes called a unital ring if there is an element. Sometimes it's denoted in general E, sometimes 1. Let me call it 1 today. If there's element 1 in R, such that 1 times x equals x, and x times 1 equals x for all x in the ring. Not every ring has to have a multiplicative unit, but a ring that does is called unital. And R is a commutative ring if xy equals yx for all x and y in the ring. So the fundamental example of a ring, the integers. Z with the usual addition and multiplication. So this ring is unital and commutative. And similarly, the congruence classes, the ring of congruence classes, ZM. So this is all the congruence classes is unital and commutative also. The rational numbers, the real numbers, the complex numbers are unital commutative rings. If K is a field, say, so these are examples of fields. I'll mention that in a moment, or maybe not even say that quite yet. If R is any ring, then R square brackets X, which is the set of all polynomials with coefficients in R, is a unital commutative ring with the usual addition and multiplication for polynomials. In fact, so this is polynomials in X. You can also look at polynomials in two variables. So this is polynomials in two variables. So you could have F equals 3x squared y cubed plus 2x minus 7y to the 19th plus 32. This is a polynomial in two variables, x and y. And the set of all polynomials in fact, any number of variables is always a commutative ring if R is a commutative ring. R is a commutative ring. If I look at n by n matrices, with coefficients in a ring R, let's say n at least two by two matrices. This is a ring that is not commutative. This is a non-commutative ring. And if R is unital, then the identity matrix, one down the diagonal and zeros everywhere else, is the multiplicative identity. Right? So these are all examples of rings. What is called an integral domain is a commutative ring with a unital commutative ring such that, for this ring R, such that if X is in R, Y is in R, and XY equals 0, then either X equals 0 or Y equals 0. So an integral domain is a ring, a commutative ring that has the property that the only time a product of two numbers is 0 is if one of the numbers, one of the elements of the ring is 0. And I should sort of prove as a little lemma, if R is a ring, X is an element of R, then X times 0 is always 0. And 0 times X is 0, right? I mean, this is not obvious in a ring. It's obvious if you're working with ordinary numbers, but how do we know that this is true? right? Why is it true in a ring that if you multiply by 0, you get 0? That's something that requires a proof. So a proof can go as follows. 0 plus 0 equals 0. So x plus 0, sorry, so x times 0 is the same as x times 0 plus 0. Because 0 plus 0 equals 0. And by the distributive law, this is x times 0 plus x times 0. So I don't know what x times 0 is, but every element in the ring has an additive inverse. So x times 0, let me add to both sides, minus x times 0. So that's x times 0 plus x times 0 plus minus x times 0, which is x times 0 plus x times 0 plus minus x times 0. An element plus its negative is 0. So this is x times 0 plus 0, which is x times 0. So this says x times 0 is 0. And the same argument works if we look at 0 times x. So this is a proof that if you multiply by 0 in a ring, you always get 0. Right? It's not obvious until you prove it. Once you prove it, you're allowed to say it's obvious. But if you can't prove it, you can't say it's obvious. So what are some examples of integral domains? Z is an integral domain. Because integers x, y equals 0 if and only if x equals 0 or y equals 0. If you multiply two non-zero numbers, you get a non-zero number. We say that an element x in a ring is a unit. R is a ring with an identity, a multiplicative identity, if there exists an element y in the ring such that xy and yx equal 1. So even though 0 is never a unit, because 0 times x is 0, which is not equal to 1. So 0 is not a unit. A field is a ring, let me call it K. It's a commutative ring such that every x not equal to 0 is a unit.
So in the field there is no 0. I mean, in the set.
Well, a field is a ring, so
Yeah.
it's an additive abelian group with a 0. There's always a 0 in every ring. You can't have a ring without 0, right? Because it's an abelian group under addition. 0 is what we call the identity element for addition. And so a field is a ring where, so 0 is never a unit. But if every non-zero element is a unit, then that commutative ring is what is called a field.
Okay.
The usual examples of fields are the rational numbers, the real numbers, the complex numbers. And the ring of congruence class is mod P for any prime P. Why is this a field? So we prove that AX congruent to B mod M, this congruence has a solution in integers if and only if B is congruent to 0 modulo the greatest common divisor of A and M. So that's a fundamental fact about a linear congruence. AX congruent to B mod M if and only if B is divisible by the greatest common divisor of A and M. So suppose that M is actually a prime number. Then the greatest common divisor of A and P, this is a number that divides P. This is either 1 or P. And this is P if and only if P divides A. So if P does not divide A, then the greatest common divisor of A and P is 1, and AX congruent to B mod P has a solution, because B is always divisible by 1. The greatest common divisor of A and P is 1. 1 divides B. So in particular, if A and P are relatively prime, then AX congruent to 1 mod P has a solution, which means if you translate this into the language of congruence classes, A plus PZ times X plus PZ equals 1 plus PZ. This is the identity element in the ring of congruence classes mod P. And A plus PZ times X plus PZ is 1. So A plus PZ is a unit in the ring of congruence classes for every non-zero congruence class. So that really is a complete proof that the congruence classes modulo a prime form a field. And if you have congruence classes mod M, and M is composite, which means not prime, then you don't have a field. So if M is composite, that means M is equal to, let's say, R times S, with R at least 2 and S at least 2, then R plus MZ times S plus MZ is RS plus MZ, which is M plus MZ, which is 0 plus MZ. So the congruence class of R times the congruence class of S is the congruence class of 0. So R can't be a unit, because if you multiplied R by something, you can't get 1. So the congruence classes mod M is, this ring is a field if and only if M is A prime. What's another example of a field? suppose we take, let's say, r square brackets x. This is all polynomials with real coefficients. And if f of x is a polynomial, not equal to 0, then at least one of these coefficients is non-zero. So let's say an is non-zero. Then what is called the degree of f is n. It's just the degree of a polynomial is just the highest power of x that occurs in the polynomial. So suppose f of x is an x to the n and so on. Suppose we have another polynomial, g of x, which is b sub m x to the m, where the degree of g is equal to m. So if you multiply f of x times g of x, just the way you learned in, I don't know, wherever you learned how to multiply polynomials, this times this, you get a term an b sub m x to the m plus n. That's the highest power of x you get when you multiply. You get the highest power of x in f, x to the n times the highest power of x in g, which is x to the m. You multiply them, you get x to the m plus n. You only have one term of this degree. This is the coefficient. an and bm are non-zero, so the product is non-zero. So the degree of f times g is m plus n, which is the degree of f plus the degree of g. So if you multiply two non-zero polynomials, you get addition of degrees. The degree of the product is the sum of the degrees. All right? So that's a very, very basic, simple, but important fact about polynomial multiplication. If you multiply it by the zero polynomial, you get 0, and the degree of the zero polynomial is said, we say it's undefined. If you have a non-zero constant, if you have the polynomial f of x equals 7, that has degree 0, right? Because f of x equals 7, but that's like 7 times x to the 0, that has degree 0. But f equal to 0 the degree is undefined. And so, for example, if f is a polynomial with real coefficients and the degree of f is 0, then f of x is just some non-zero constant. And if I let g of x be equal to 1 over a0, which is another, if a0 is non-zero, so is 1 over a0, then f of x times g of x is a0 times 1 over a0 is 1. So a non-zero constant polynomial is a unit in the ring of polynomials. But if the degree of f of x is some number n greater than or equal to 1, so f of x is an x to the n and lower order terms, then if g of x is not 0, and I multiply f of x by g of x, the degree of this product is the sum of the degrees. This is n plus something. So that's at least n, which is greater than 0, at least 1. So the product of two polynomials is not a constant unless both of the polynomials are constants. So no polynomial in this polynomial ring of degree at least 1 is a unit. So in particular, R of X is not a field. So polynomial rings with coefficients in R, they don't form a field. Any questions about this? This is sort of just basic general information about rings. Now, if you remember from calculus, you have what are called rational functions. That's a quotient of polynomials, like x cubed plus 7x plus 2 over x squared plus 19. This is a rational function. It's one polynomial divided by another polynomial. And in Math 175, you learned how to differentiate this, for example, using the quotient rule and so on. And suppose we let R round brackets x be the set of all rational functions with coefficients that are real numbers. So these are polynomials of the form P of x over Q of x, let's say, where P and Q are polynomials. And the set of rational functions is a field. What is the inverse of x squared plus 1? It's the rational function 1 over x squared plus 1, right? This is a rational function. And x squared plus 1 times 1 over x squared plus 1 is 1. In general, if you have P of x over Q of x, so Q of x, the denominator, is never 0. And this is 0 only if P of x is 0. So suppose P of x is different from 0. If I take this rational function and multiply it by the rational function Q of x over P of x, everything cancels and we get 1. So R of x, rational functions, is a field. That's another nice example of a field. So, any questions so far? There's a lot to become familiar with here. Okay, so let's just draw an analogy. When we study groups, we learn about subgroups and normal subgroups. And in the case of rings, there are subrings of a ring and what are called ideals. So for example, so the definition is, so let R be a ring, a subring of R is just a subset S contained in R, such that S is also a ring with the same operations of addition and multiplication. So for example, Q is a ring, the rational numbers. The integers are contained in Q, and Z is a subring of Q. under the usual addition and multiplication. C is a ring and it's a subring. Suppose I take R to be M sub 2 of, let's say, R. All 2 by 2 matrices. That's a ring. Suppose I take S to be all matrices A, B, 0, D. All matrices where the lower left-hand coordinate is 0. So I claim this is a ring. Well, it has to be closed under addition and multiplication. What about addition? If I take A1, B1, 0, D1, and A2, B2, 0, D2, and I add, addition is coordinate-wise, A1 plus A2, B1 plus B2, 0 plus 0, D1 plus D2, 0 plus 0 is just 0. This is an S. And if I were to subtract, I still get the lower left-hand coordinate 0. So this set of matrices, all by itself, is an additive abelian group. But is it closed under multiplication? Let's see. I take A1, B1, 0, D1, A2, B2, 0, D2, and I multiply this. I get A1, A2, A1, B2 plus B1, D2, 0 plus 0, and 0, B2 plus D1, D2. So if I multiply 2 matrices with a 0 in the lower left-hand coordinate, I get another matrix with a 0 there. So this set of matrices is closed under multiplication also. And you can also note that the identity matrix 1, 0, 0, 1, it also has a 0 in the lower left-hand coordinate. So this is an S. So this is a nice subring, the ring of 2 by 2 matrices. So when we studied groups, we learned about group homomorphisms. So a function phi from a ring R to a ring S is a ring homomorphism if phi of x plus y is phi of x plus phi of y, and phi of x times y is phi of x times phi of y for all x and y in the ring R. So this is exactly the property that a group homomorphism had to satisfy. And we have a ring homomorphism if this similar property holds both for addition and also for multiplication. And if R and S are rings with 1, we also require that phi of the identity element, I'll call 1 sub R, the 1 in the ring R gets mapped to the number 1 in the ring S. And what is called the kernel of phi, it's all x in R such that phi of x is equal to 0. So we know, because phi is, among other things, an additive abelian group, because R is an additive abelian group, and S is an additive abelian group, and phi, if it satisfies this first property, is a group homomorphism, this is automatically an additive subgroup of the ring R. But we can also observe the following. If X is in the kernel of phi and R is any element in the ring R, then phi of Rx is phi of R times phi of X. But phi of X is in the kernel. So phi of X is 0, and you multiply by 0, you get 0. So Rx is in the kernel of phi. And similarly, phi of XR is phi of X times phi of R is 0 times phi of R is 0. So XR is in the kernel of phi. So the kernel of a ring homomorphism has the property that if you multiply it on the left or the right by any group element, the resulting product is still an element of the kernel. And a subset of a ring with this property is called an ideal. So an ideal of a ring R is an additive abelian subgroup. That is, R is a ring under addition, so a group under addition. So it's an additive abelian subgroup. Let's call it I, such that Rx is in I and XR is in I for every element X in the ideal and R in the ring. So an ideal in a ring is analogous to a normal subgroup in a group. Both of them are the kernels of homomorphisms. The kernel of a group homomorphism is a normal subgroup. The kernel of a ring homomorphism is an ideal. Now, it's often important in algebra to look for the smallest ideal that contains some given set of elements. So suppose I let S not be a subring, but simply a subset of a ring R. What is called the ideal generated by S, which is usually denoted by S inside of brackets, is the smallest ideal of R that contains S. And it's also another way of describing it is the intersection of all ideals of R that contain S. And in the simplest case, suppose S consists of just one element, A. So, and let's suppose that R is a commutative ring. Then the subgroup, the ideal generated by S, I'm just going to write that as RA, This is the set of all elements of the form R times A, where R is an element of R. So I claim this is an ideal that contains A. So notice that R, let's say, is a unital that has a 1 in it. So 1 times A, which is A, is in this set. So RA contains A. And if I have two elements, R1A and R2A, and I add them, I get, by the distributive laws, R1 plus R2 times A. So this set RA, all multiples of A, is closed under addition. And R1A times R2A, I can write that as R1A times R2, all times A. If I call this some element R, this is another element, R times A. It's another multiple of A. So RA, if I multiply, well, this just says it's closed under multiplication, but an easier thing is that if I take X in R and RA in RA, then X times RA is XR times A. So that's a multiple of A. So if I take anything in this set and I multiply it by a ring element, I get another element of this set. So this is really the simplest ideals there are, an ideal generated by a single element. And such an ideal is called principal. So a principal ideal is an ideal that's just generated by one element. And some rings have the property that every ideal is a principal ideal. Now, what is called a principal ideal domain, or PID, is an integral domain in which every ideal is principal. And two basic examples of this are the integers. Every ideal is generated by a single element, and the ring of polynomials with coefficients in a field, like R of X. And for both of these, you use the division algorithm to prove that they're principal ideal domains. All right. So this is all kind of review of what we did on Monday. Let's see. Recall that a field is a commutative ring with one where every non-zero element has an inverse. So here's a very simple theorem. It's nice to prove. That K be a field the only ideals in K are the trivial ideals, the ideal that consists just of 0, and the ideal which consists of every element in the field. So proof. First of all, 0 is an ideal because 0 plus or minus 0 is 0, and x times 0 is 0 for every x in the field. So the set consisting just of 0 is closed under addition and subtraction, and it's closed under multiplication by an arbitrary field element. That I be an ideal which is not 0. In that case, then, if it's not 0, there's some element, A, in the ideal, A not different from 0. But then A inverse is in the field, and so A inverse times A is in the ideal, which means 1 is in the ideal, because 1 is A inverse times A. And if 1 is in the ideal, x times 1 is in the ideal for all x in the field, and x times 1 is x. So the field, the ideal, contains every element. So every element of the field is in the ideal, which is itself contained in the field. So the ideal has to equal the field. So if an ideal is not 0 in a field, then it must be the whole field. So there are no non-trivial ideals in a field. Here's an interesting problem in the book. This is problem 6.2.2. Suppose I define a function phi from the polynomials with real coefficients into the 3 by 3 matrices R. So I want to define this function as follows. If f of x is equal to, let me write the polynomial in increasing powers of x, a0 plus a1x plus a2x squared plus a3x cubed and so forth up to, let's say, a(n)x to the n. That's my polynomial. Define phi of this polynomial f to be the following 3 by 3 matrix. A0, A1, A2, 0, A0, A1, 0, 0, A0. So this assigns to every polynomial a matrix. So for example, if f of x were equal to 2 plus 4x plus 7x squared plus 3x cubed, phi of f would be what? It just looks at the first 3 coordinates, 2, 4, 7, 0, 2, 4, 0, 0, 2. Okay. So this polynomial gets sent to this matrix. This function phi only looks at the quadratic part of the polynomial. Why is this a homomorphism? Let's just check multiplication. So suppose this is f of x, and suppose g of x is equal to b0 plus b1x plus b2x squared plus b3x cubed up to some b sub m x to the m. If we multiply f of x times g of x, what do we get? Well, you have to be able to multiply polynomials. The constant term is A0, B0. The linear term is A1, B0 plus A0, B1 times X. The quadratic term, when you multiply these, you get A0, B2, A1, B1, A2, B0. That's the quadratic term. And then there are higher powers of X. So let's see, what is phi of F times phi of G? Phi of F is the polynomial, is the matrix A0, A1, A2, 0, A0, A1, and 0, 0, A0. And phi of G, this is G, is the polynomial, is the matrix B0, B1, B2, 0, B0, B1, 0, 0, B0. Let me try to multiply these out. I get A0, B0. Let's see, what's the first column? Second row, first column, I get 0. Second row, third column, I get 0. First row, second column, I get A0, B1 plus A1, B0. First row, second column, I get A0, B0. Second row, third row, second column, I get 0. And first row, third column, I get, actually what I get is exactly this. And second row, third column is A0, B1 plus A1, B0. And third row, third column is A2, B0. And if you notice A0, B0, that's the first coefficient of FG. A0, B1 plus A1, B0, that's the second coefficient of FG. And this is the third coefficient. So this is exactly phi of F times G. So this function phi defined in this curious way, which is assigns a certain matrix to a polynomial, preserves multiplication, and it's very quick to check it preserves addition. So it is a ring homomorphism. And what is the kernel of phi? So F is in the kernel of phi if and only if phi of F is equal to 0, but this is phi of F. It's equal to 0 only if the first three coefficients are 0. So if and only if phi of X is a polynomial which starts with a cubic term. It's all polynomials for which the constant, linear, and quadratic terms are 0. And the set of all such polynomials does form an ideal. So that's an interesting example of a ring homomorphism. Let's look at another example. This is problem 6.2.7. Suppose R is the set of all 3 by 3 matrices that are upper triangular. That means, let's say this is A11, A12, A13. 0, A22, A23, 0, 0, A33. So this is the diagonal, and the non-zero elements are everything on or above the diagonal. Everything below the diagonal, that's these three numbers, those three coordinates are 0. So these matrices are called, these are 3 by 3 upper triangular matrices. Suppose we let I be the set of all matrices which are 0 on the main diagonal and 0 below the main diagonal, and it's only above the main diagonal that you might have non-zero elements. So we claim that this set I is an ideal of R. So why is that? If I add two matrices of this form, you don't get a non-zero element when you add 0. So this is closed under addition and subtraction. So this is an additive abelian group. But why is it closed under multiplication? Let's just check. Maybe let me use different letters here. Let me call this B12, B13, B23. So suppose I take a matrix A11, A12, A13, 0, A22, A23, 0, 0, A33. And I multiply a matrix like this, 0, B1, B2, 0, 0, B3, or this is B1, 2, this is B1, 3, this is B2, 3, and this is 0, 0, 0. So if I multiply this, first row into first column, that's 0. Second row into first column is 0. Third row into first column is 0. What is the second row into the second column? I get 0, 0, 0. What's the second row into the third column? Sorry, that's not what I want. What is the third row into the second column? This times this is 0. What is the third row into the third column? This is also 0. So whatever I get, I have zeros in these 6 places. And here I have something, whatever I get, they could be 0, they can be non-zero. But in any case, this set of matrices with zeros on and below the diagonal is closed under multiplication on the left, and we can check also on the right by any upper triangular matrix. So this is going to be an ideal. Okay, well, there is a bit to think about, and well, I don't want to push too far ahead because we're really done for the semester. I will have a review sheet that I will send out, and I'll go over it in class on Monday. And let me remind you that I do have the problem sessions. There's one today. There's one tomorrow. I'll set up one on Friday also, and there'll be several problem sessions before the final exam. And I encourage you, as you study the material, if you have questions, to log into a problem session and ask. That is always the best way to learn what's going on. Any questions before we stop for the morning? Okay, so this is recorded, it'll be posted in a few minutes, and see you perhaps in a problem session, if not, class on Monday. Okay. Be well.
Thank you.